In this video, we will look at hypothesis testing and look specifically at case 1, where we have a normal population with a known standard deviation. So in your study guide, you will see the pages in your textbook you need to read and what you need to be able to do here. So there are 3 cases that we will consider in section 9.2, and then you will also need to be able to determine sample size based on alpha and beta, which we discussed in the previous video. Now let's just go through some basic testing procedures. So 9.2, we are going to look at tests for the mean for 3 different cases. So the first case, like I mentioned, is for normal population with a sigma known. This is of course not very realistic in general, but there are cases where we might know where the population standard deviation is. So there might have been a trend over the last few years, and we believe that trend continues. Then the second case will be where we have large samples and sigma is unknown, and with large samples you should be thinking central limit theorem. So notice in the first case we know the data is from a normal population. In the second case, because we have a large sample, we can depend on the central limit theorem. Now the third case is going to be if we have small samples and sigma is unknown, and we'll go through the test procedure there. So for this first case, we'll also consider the link between alpha, beta, and sample size, and how to do calculations for beta. So that will be in the next video that we look at. This video we'll just go through the test procedure. Then also in this chapter, we will still do the section 9.3 where we do tests for proportion, and we'll do some additional material as well where we're looking at tests for variance. And then lastly, we will also do p-values, which will then cover all of the different scenarios that we've done. So, but p-values sounds like a lot to deal with, but it's actually a really simple concept. Now let's look at the general procedure. So in the general procedure, we start by looking at our first step, which is just the definition of our hypotheses. So I've written it quite generally here with the theta, but of course that could be mu, it could be p, it could be sigma or sigma squared. And like we said before, your null will always have an equal sign. Your alternative will be greater than, less than, or not equal. So those are our 3 situations that we will deal with. Then our second step, which we looked at in the previous video as well, looks at identifying what sample statistic we are going to use. Then we look at the sampling distribution of that sample statistic, or a function of that sample statistic under the null hypothesis, which is then called our test statistic. So that function of our sample statistic is called a test statistic. Then there will be a decision rule, which is based on the distribution of that sample statistic, or the test statistic, and then we will choose alpha, which is the more important risk, as we saw before, and we will give a rejection region. Then we will calculate our test statistics, so we'll gather our data. So again, notice we decide on our hypotheses to test before we gather our data. And then we will, once we've calculated our test statistic, we will make a decision by comparing the test statistic to the critical value that we also got from the distribution of the test statistic, and we will decide whether to reject the null or not reject the null. And then lastly, we will make a conclusion, which is always in terms of the problem statement, and it is in words. So you should think about this as if you had to explain your results of your test to someone, you're not going to do it with a bunch of math symbols. You're going to put it in words so that anyone can understand what you're saying. So in this fourth step, we said that you need to make a decision, and that decision always has to be reject the null or do not reject the null. And first we'll just look, before we get into our tests, at why it cannot be accepting the null. So let's say, for instance, we have a scenario. We have a man who is dressed quite poorly, clothes are maybe a bit torn, a bit dirty, all of that. So our null hypothesis might be that the man is poor, and we want to prove that the man is actually not poor. So let's say, for instance, we gather our data. Now, we see that this man walks to work. Does that mean that he is poor, or does that mean that he's just trying to save on transport costs? Or maybe he is just interested in getting a bit more exercise. So is that enough evidence to say the alternative is true, or does it not support the alternative? Next, we might observe that he takes a packed lunch to work. So is that because he can't afford to buy lunch at work? Or is it because he doesn't like the food that he can get at work? So again, does it support the alternative, or is it not enough to support the alternative? So if we observe these things, we still don't have reason to reject the null hypothesis. But we also can't accept the null hypothesis because we don't know all the facts about this man. Now, let's say next we observe that this man owns a bank account that contains R500,000. Then we might have enough reason to say we reject the null hypothesis. So we never accept the null hypothesis because let's say we only had those first two pieces of information, then it might not fully support the alternative, but it doesn't mean the null is true either. So we either reject the null hypothesis or we don't reject the null hypothesis. But we never accept a null and we never accept an alternative because it's based on evidence and we might not have all the evidence. So the only time we really can say that a hypothesis is true is if we've actually collected data on the entire population and we're observing the entire population. Then we could say, okay, now we know enough. We have all the facts. We can make a clear decision. And we can't be wrong because we've observed everything. But any other time, we don't like being wrong, so we can say we reject or we don't reject the null, but we don't ever say that we accept something because then we could be very much wrong. All right, so let's move into our first test. So we have a test about the population mean, normal population with known sigma. So an example of where sigma could be known, I've observed over the years of teaching, for instance, I've kept track of how students performed in semester tests. And for a specific module that I used to teach, I actually observed that the standard deviation of the marks in their tests, the mean was always different. Every year the mean would differ, but the standard deviation was always roughly 12 to 13%. So that is an example where we could say, okay, well, we've observed this pattern. We have no reason to believe that it's different. So we'll take that sigma from the past and still accept that that is still our sigma. We just think the mean shifts around a little bit, but the distribution around the mean stays the same. That's what it basically means. Now, it's not the most realistic thing always, but there are cases where that does apply. Now, again, first step will always be to formulate our null and alternative. So our null is going to be that the mean is equal to some value. And again, that mu naught, the null value or the hypothesized value, is just a placeholder for a value that we're going to plug in there. Then our alternative will be greater than, less than, or not equal. Now, step 2 is to look at a sample statistic. So we commonly, when we do tests for the population mean, we just use the sample mean as the basis for that test. Now, if we have the sample mean, we know the distribution of the sample mean. Remember, if our x values are from a normal distribution, then we know that x bar will also be normally distributed. And if we standardize x bar using its mean and its standard deviation, then we end up with z having a standard normal distribution. So this distribution that we're working with is under the null hypothesis. So we assume the null hypothesis is true, which then means that we have a mean of mu naught and a standard deviation of sigma over root n, so that we learned in one of our previous chapters. And then if we standardize, we of course get to the standard normal. Now our decision rule, we would need to know what alpha is, so we would need to know what risk we are willing to accept of making a type 1 error, and that's a given. If we don't give you a value for alpha, the common values of alpha that we usually use will be 0.01, 0.05, and 0.1. These are the ones that are used most in practice. But we can ask you for any level alpha, we can ask you to go set up a decision rule. So you need to understand where these rules, or how to use these rules to go find your rejection region. And if we don't give you an alpha, you can generally assume that alpha is 0.05. We will be happy with that one. Then our rejection rule would be, depending on whether it's a left-sided, a right-sided, or a two-sided test, to reject the null if our test statistic is larger than Z alpha, and that's in the case where sigma is, or where we're testing a right-sided test. Left-sided test, we will have a left-sided rejection region, and a two-sided test, we will have a two-sided rejection region. So here you can see we have a lower limit and an upper limit, and if your test statistic is either smaller than the lower limit or larger than the upper limit, then we will reject the null hypothesis. Then we need to go and calculate our test statistic. So we've already spoken about this test statistic, how we're going to use it to make our decision. This rule is, of course, only based on what the alternative tells us. And then we do our calculations, and we can then go compare our test statistic to our critical value, and we can reject the null or we don't reject the null, and we make our conclusion. So one important thing, always draw a graph. Whenever you do a hypothesis test, draw a graph, put your rejection region on the graph, put your test statistic on the graph, and that way you can visualize the problem and you are a lot less likely to make mistakes. Now, let's look at the three different graphs. So let's say we have a right-sided test. Right-sided because our test statistic, not our test statistic, because our sign in the alternative is a greater than. That means that we have a right-sided test, and that means that we will have a right-sided rejection region. So we want to test whether the mean has increased. So an increase will be looking for a value which is larger than a specific cutoff point. So this will be Z alpha. Now, if we did a left-sided test, again, we can draw our graph, and because it's a left-sided test, because this says less than in the alternative, this will be minus Z alpha. And if we do a two-sided test, we end up with two rejection regions. And here we have Z alpha over 2, and on this side will be minus Z alpha over 2. So you can see that we still have alpha in each of the tail ends in the first two cases, and in this case, because it's a two-sided test, we need to split alpha into the two tail ends when we do our or find our rejection region. Now, you just need to remember to do that split only for the two-sided ones, and to find these different Z values, it's just percentiles from the standard normal tables. So in your textbook, there's actually a sketch, figure 9.2, which explains all of this. So you can see again, in each case, the alpha, our probability of making a type 1 error, is shown in the rejection region. So here where we have two rejection regions, we need to split alpha into the two sides so that our overall probability of making a type 1 error remains alpha. Now, assumptions for this test, like we already said, our sample is from a normal distribution. We know sigma. So those are our two assumptions. So whenever you get a problem in a test or a tutorial or wherever, always read through the question, highlight all the assumptions, and then go match it to your test. So it's a good idea to do a tree diagram where you kind of go through this process to decide which test is the appropriate one to use. So you put all of your assumptions on a tree diagram and you see to which test that leads you. Now, in this case, our null hypothesis, like we said, is that the mean is equal to some value. We can calculate our test statistic, which is actually just standardizing our sample mean. So nothing new, nothing strange. You've actually done this before. Then our alternative can be one of these three. For greater than, you have an upper tail test. So greater than rejection region. For a left-sided test, you have a rejection region in the lower tail, and for two-sided, you have a two-sided rejection region. Now, in your textbook, they do go through these steps a little differently from what we've shown you in the videos. So the steps themselves don't matter so much what we call them, how many steps we break it into. It's just important that you understand how to apply them. So in your textbook, they start by saying, firstly, identify the parameter of interest. So are we dealing with mu? Are we dealing with p? Are we dealing with sigma squared? Are we dealing with sigma? Are we dealing with something else? What parameter are we dealing with? Because you can't do a test if you don't know what you're interested in. Then you need to determine the null value and state the null hypothesis and state the appropriate alternative hypothesis. So these steps together are basically what we called your first step. Now, next they say, give a formula for the computed value of the test statistic, a whole bunch of things. Basically, what it boils down to is give your distribution of your test statistic under the null hypothesis. So look at what your null hypothesis is and figure out the distribution from that. And then find your rejection region for a given level of alpha. So these two steps together kind of form the second step that we showed you. Then next, it says compute any necessary sample quantities, substitute into formulas, all of that. So that is like our third step that I showed on the previous slide. Then deciding on whether H0 should be rejected. So this is your decision, and then stating the conclusion. So this is like 4 and 5 on our previous slide. So this is basically the process. It doesn't matter into which steps we break it. We'll illustrate it now with an example. So let's look at one of the examples in your textbook. So we have here the melting point of each of the 16 samples of a brand of hydrogenated vegetable oil was determined, resulting in a sample mean of 94.32. Assume that the distribution of melting points is normal with sigma equal to 1.2. So you can see here, there's our first assumption, normality. We know what sigma is as well. And always, always, always go and lift out all of this important information that you're given and just go summarize it for yourself, because then you don't need to read all of these words multiple times. You're not going to miss something. Just write down what you have, because that will give you a feel for which direction the test is heading in. Now, in part A of this question, they ask you, test the null mu equal to 95 versus the alternative that mu is different from 95 using a two-sided test with alpha 0.01. So there I've put my alpha as well. So I've written my null and alternative here. So that's our step 1 completed. Now we can think about our distribution. But first thing I want to do is actually define my variable. So if you start by writing down what your variable is, you're also a lot less likely to misunderstand the question. So we have here x is the melting point of hydrogenated vegetable oil, and x bar is the average melting point for a sample of 16 hydrogenated vegetable oils. So if we asked you questions now about the probability of x versus the probability of x bar, you can see that the wording of this definition tells us which variable we're working with. Now next, we want the distribution of our test statistic. And for these tests, we did some tests in 9.1 where we were working with x, but that's not something we really do in practice. So we are going to work not with x or with x bar. We're always going to standardize, because it's easier when we're working with z, because it always has a standard normal distribution. It's easier to understand our test results. So in practice, what we do is what's done in section 9.2. So first thing I want to do is write down my test statistic. So I have a test statistic under the null hypothesis. Z is calculated as x bar minus mu naught over sigma over root n. Because x bar has a normal distribution with mean 95 and variance 1.2 squared. So if we standardize, sorry, 1.2 over 16 root 16 squared. And then if we, sorry, this is the distribution that I wrote here for x bar. This is not for z. Let's just correct that. So this is then the distribution of x bar, not of z. So z's distribution is going to be normal, 0, 1. So we start with x bar, which has this distribution, and then when we standardize it, this has a normal 0, 1 distribution. So this is the distribution of x bar under the null hypothesis. Apologies for that error. Now we have this distribution, so we are going to work with z, not with x bar. So when I choose my cutoff point or my rejection region, in this case, we are not going to work with values from the distribution of x bar. We're going to go straight to the standard normal. So to do that, let's go look at our standard normal curves. So we've said here that alpha is 0.01, and we've specified that our alternative hypothesis is that the mean is not equal to 95, which means it's a two-sided test, which means that this alpha actually needs to be split into the two different tail ends. Now, that means that if I have a sketch here of the normal distribution, excuse this, my writing tablet seems to like making pointy ends. So let's say I have let's see if I can get it to the eraser to work. And we can just draw a better sketch. And let's try again. Okay, so there we have our curve, which means that this area here, along with this area here together, should be alpha. So that area in there should be alpha over 2. And that area down there should be alpha over 2 as well. So that means that my percentile here, this is actually going to be z of 0.005. And then this will be z technically of 0.995. So 99.5th percentile. Now, if you look at the table 4.1 that you have in your textbook, then you'll see that this tail area specifically refers to a tail area of 0.005, and that is the same as the 99.5th percentile. So that value there is the one that we're interested in. Now, we could also go to your standard normal tables and go look for the 0.005 on your tables. And if we look here, we're going to find 0.005 is in between those two values. So you could have used, for this lower value, either minus 2.57 or 2.58, or you could have said, well, this is midway in between, so let's use 2.575. So that's an option as well. Or you could have gone to the last row of your t tables. Remember the t distribution, if we have infinite degrees of freedom, it's actually the same as the standard normal distribution. So we could have used the standard normal table, the t tables as well, to find this value for the standard normal distribution, and looked at a tail end of 0.005, and there we actually get the best value to 3 decimal places, 2.576. So that's another shortcut way of finding this value. So go back to your tables and check that you can get to the right z value using all three of these methods. Now, if you go back to the question, that means that we have our two critical values. These are called critical values, which are just our cutoff points. So I've used the one from the t-table because it's the most correct one. But like I said, if you had used minus 2.57 and 2.57 or 2.58, that would have been fine as well, or the 2.575. We're not going to be too fussy about that. Just know how to find these values. Now, we have our rejection region here. Next thing we'll do is we will go find our test statistic. So our test statistic, to do the calculation, we already have all of these values we need to plug in. Notice how I've now gone to a lowercase test statistic here, because we are now going to do calculations. We're plugging the values in. So if I plug them in, I end up getting a value minus 2.27. So that is the value of my test statistic. And if I go put it on my graph here, it's going to lie somewhere over there. So we can immediately see our test statistic is not in the rejection regions. It doesn't lie to the left of minus 2.576. It doesn't lie to the right of 2.576. It is in between the two, which means I will not reject my null hypothesis. So my decision here, when I make the comparison, because it lies between these two critical values, we do not reject the null hypothesis. We don't accept it. That will never ever be an acceptable answer. We will say we do not reject the null. And then our last step is just to make our conclusion. So it's best practice to always mention what significance level we used in our calculations, and then give it in words, as we already pointed out. So our conclusion is always in terms of the alternative. So we never say the words in terms of the null. We will always put the alternative in words when it comes to the conclusion. So in this case, it means that the mean is different or not different. We don't have evidence to say that the mean is different from 95. So there I've written it out. At a 1% level of significance, we don't have the evidence to support the alternative. So we don't have evidence to say that the mean melting point differs from 95. So you can see this is in terms of the alternative, and a conclusion should always be in terms of the alternative. It's never in terms of the null. So we have evidence for the alternative, or we don't have evidence for the alternative, which means we need to put the alternative in words like we've done here. So now let's look at this problem from a different perspective. Let's change a few values around. So we now have that I've just changed our alternative. So this is obviously not question A anymore. It is now a different question altogether. So this is not in your textbook. But I've said here, let's test a null that the mean is 94 versus that the mean has increased from 94. And again, let's do it with a 1% level of significance. So again, we are working here with X bar, and our test statistic again has a normal distribution, a standard normal distribution, and that is because X bar has a normal distribution with a mean of 94 and this variance under the null hypothesis. So again, under the null just means that we assume that the null hypothesis is true, and that would mean then that X bar has a distribution which is centered at 94. So next we will want to get our critical value. So we go to our tables again, and in this case, because it's an upper tail test, we've said here that the alternative in this case is that mu is greater than 94. So now we only have a rejection region on the right hand side because that says greater than. So all of alpha will go in there. So this is going to be our 99th percentile. So in your textbook though, it is using notation which can maybe be slightly confusing. I'm going to write it the way your textbook would have done it. So it's Z of 0.01. usually with the normal tables, we would write 0.99, but in the context of hypothesis testing, I've noticed that your textbook is using slightly different notation. So for the hypothesis testing, the 0.01 actually refers to the area in the tail end, so not necessarily area to the left. So just be aware of that and don't get confused by it. It's just for the context of hypothesis testing that they change their notation a little bit. Now that means that we are looking for a tail end of 0.01, and that means our percentile is the 99th one, which is what we already said. So that Z value is 2.33. Now, if we look for that in this table, I obviously didn't put the right tables here, so I'm going to skip this table and let's move on to the t-table. So we would have looked for a probability here of 0.01, but I accidentally included the wrong table. I am sure you will find the right value though. Now, if we look at the critical values from the t-tables, remember again, infinite degrees of freedom is basically the same as a standard normal. So we go look for 0.01 in the tail end, and we get the value to 3 decimal places, which is 2.326. So if we go back to our question, we can add our rejection region onto this graph. So you can see there's many ways of finding these rejection regions. You could of course go and get it to more decimal places if you used R or Excel, and I want to challenge you to go and see that you can get this value in R specifically, so that everything you learned in practical 2 will help you to do that. Now again, test statistic, if we do our calculation here, Z is just this calculation, just standardizing our X bar value, and we end up with a test statistic of 1.07. So our test statistic is somewhere over here. We can again see it's not in the rejection region, which means we won't reject the null hypothesis, and we can make our conclusion. So again, our conclusion is going to be in terms of the alternative. And it's just good practice to always mention our significance level so that we know what level of risk we assumed when we made this conclusion. So at a 1% level of significance, we do not have enough evidence to conclude that the mean melting point is more than 94. And notice, more than 94 is in terms of my alternative. And we don't have evidence to support the alternative because we didn't reject the null hypothesis. So if I'd rejected the null hypothesis, I would have had the evidence to support the alternative. So in that case, we would have said we have evidence to conclude that the mean is more than 94 and mean melting point. So remember, in words, this is a nice straightforward sentence. So another way of doing hypothesis testing, which is good to be aware of, is using confidence intervals, because there's a very strong relationship between these two concepts. So this is only explained in a single example in your textbook, but it is important that you understand the logic behind it. So let's say we're looking at a two-sided test. So we have a two-sided hypothesis test. We know it's two-sided by looking at the sign in the alternative. Now, if we drew a sketch of this, then we can see what it looks like, where our rejection regions are, and you can go and indicate your test statistic on this. Now, that would mean that we will reject the null hypothesis if Z, our test statistic, is less than that lower critical value, or if Z, our test statistic, is larger than the upper critical value. We don't reject the null hypothesis if we have a test statistic that falls in between the two critical values. So that means we can turn this problem around and we can say, well, that just means that we don't reject the null hypothesis if Z is between these two critical values, and we can replace Z with how we calculated it. So I've just put my test statistic in here. And now we can restate this. If you solve now to get mu naught in the middle of this interval, then you end up with these two limits. And if you look at this, you should be thinking, but this is just the lower limit of my confidence interval for the mean, and this is my upper limit for the confidence level of confidence interval of the mean. So you can see that if my hypothesized value falls within these two limits, or between these two limits, then we won't reject the null hypothesis. So in other words, like we said, this is just a confidence interval that we calculated in chapter 8. Now, let's say we've give you a confidence interval for the mean. So we just denoted it here by LL and UL. Then our rejection rule would be, if my hypothesized value is in the interval, we don't reject the null. We just saw that when we wrote the previous statements. But if my hypothesized value is outside of that interval, then we'd reject the null hypothesis. And that actually makes a lot of sense, because if you see the hypothesized value in the interval, we know, let's say we've done a 99% confidence interval for the mean, then we are 99% confident that the mean is in that interval. So if the hypothesized value, which we think is the mean, is in that interval, then we have no reason to think that that hypothesized value is not the population mean. So I hope that makes sense. So we're pretty sure the actual population mean is in this interval. So if that value doesn't fall in the interval, then it doesn't make sense that that could be the population mean. So this holds for other parameters as well, and we'll look at that later on again. Now, in general, what this just means is that if my null value lies inside the interval, we don't reject the null, because it makes sense that it is the population parameter. If the null value is outside the interval, then it doesn't make sense that it's the population parameter, so we reject the null in favor of the alternative. Now, confidence intervals. Let's see what your textbook says. It will exclude a value when the corresponding test rejects the value, and that is really important. So you should always, if you do a test with a confidence interval and you do it with a hypothesis test, you should always get to the same results. But what's really important is to recognize that if you are dealing with a two-sided test, you need to work with a two-sided confidence interval. If you're dealing with a one-sided test, you need to work with a one-sided confidence interval. So if we can approach this problem again from the perspective of a right-sided test. So let's say we are doing a right-sided test. Then we will reject the null hypothesis when our test statistic is larger than Z alpha. So here, this is a sketch to visualize that. Now, that means we will reject the null hypothesis when this test statistic, so x bar minus mu naught over sigma squared over n, the square root of all of that, is greater or equal to Z alpha, the critical value we get from the tables. So we can go and rewrite this in terms of mu naught, and we end up saying, so we will reject the null hypothesis when mu naught is less than this value over there. So if we did a confidence interval for an upper tail test, we always have a lower limit and the interval goes to infinity. And if mu naught is not in that interval, so in other words, if it's less than that lower limit, then we will reject the null hypothesis. If it falls inside that interval, then we don't reject the null hypothesis. So in other words, an upper tail test or an upper tail confidence interval always has a lower bound, which makes sense because you're thinking that the value is larger. So it must be larger than a certain value to be considered larger. Now, we can do the same kind of thing for a lower tail test. So we can have here less than, and using the same logic, we say we'll reject the null if our test statistic is less than a negative critical value, or the negative critical value. And I've written it a little bit differently this side. I'm used to more using the notation sigma over root n. You can use either way, same thing. And we can just go and solve this again for mu naught, get mu naught on its own. And there we forgot to flip this sign. So that has to be a greater than. It's always interesting. I experience the same thing when I'm teaching on campus. You always find your mistakes on your slides once you are teaching the class. So that means that if mu naught is larger than this upper bound, then we will reject the null hypothesis. So we expect the mean to be in this interval, and if it's outside that mu naught of that interval, then it doesn't make sense that it is the population mean. So to show you these questions that we've looked at from a confidence interval perspective, we already saw that we weren't going to reject the null in both these cases. So because this is a two-sided test, the first one, we are going to use a two-sided confidence interval. So I want you to first just do these two questions on your own. So pause the video now, and then you can look at the answers afterwards, and you can see whether you understood everything correctly, especially the second question. Now, if we do this calculation, you will notice that the z value that we use in our confidence interval calculation is actually the same limits that we had, the critical values or the cutoff points that we had in our hypothesis test. So you can see that link quite clearly. And if we do this calculation, we get this confidence interval. And you can see that value of 95 is contained inside this interval, which means that we do not reject the null hypothesis. It makes sense that the mean could be 95 because the mean or 95 falls inside this confidence interval. Now, if we are doing a upper tail test, an upper tail test always has a lower limit when we do a confidence interval. And notice here, we are no longer splitting alpha in two because it's a one-sided test. So if we calculate our confidence interval, we end up with this confidence interval. And again, that 94 falls inside this interval, which means we will not reject the null hypothesis. So a final question that I'm going to leave for homework for you guys is to go and test whether the mean is less than 96. So I want you to do this with a confidence interval, but then also go do it with a hypothesis test and make sure that you get to the same solution both times. And then some extra homework is just working through example 9.6 in your textbook, and then also please go do questions 15 and 18, just A to C at this point.